Now that we know what vectors are, let's talk about some of the operations we can do with vectors. How can we add vectors? So for example, if I have a vector A and I have a vector B here, let's put the arrows on top. They should have the arrows on top. What does it mean to add a vector A plus vector B? What does that give us? And the answer is here. It's already on your page. A is a vector that goes like this. So if we're following the path, it goes like this. And then B is the vector that goes like this. So essentially what it's asking for what's the distance from the beginning of that path to the end of that path? What is the straight distance from the beginning of that path to the end of that path? And that's what the sum of A and B is. It's really the distance from the beginning to the end. We often call the sum of vectors a resultant vector, R. And that stands for resultant. So the answer to this problem, the vector A plus the vector B, is actually the vector R. So you can notice the answer to an addition problem of vectors is another vector. You get another vector out of it, and it's basically the vector that represents the beginning of that path to the end of the path. Okay, so let's do some math with this. What's a vector that's equivalent to DC plus CA? And remember, these are supposed to have arrows on them, all of them. I'm not going to add them in because it's a lot of work, but yeah, Google just doesn't let you put the arrows on top. So let's not worry about that right now. DC to CA. Or sorry, DC plus CA. So let's think about what those two vectors are. DC is the vector that goes from D to C, right? And CA is the vector that goes from C to A. So if we think about that path, following along, starting at D, going to C, and then going to A, basically what it's asking for is what's the vector that goes from the beginning of that path to the end of that path. And if you'll notice, the answer to this is dA. The resultant vector is just dA, right? Because it goes from the start of that path to the end of that path. Okay, next one. Do it in another color. BD, so BD comes down like this, plus DC, DC goes like this, plus CA, CA goes like this. So again, we started our path here at B, and we're finishing our path here at A. So what's the answer to this? Well, it goes from start to finish, it's just BA, right? Because it goes from B to A. That's the answer. Let's keep going. Another color. Let's use red. AD plus DC plus CB plus BA. Ooh. What do you notice? We're back to where we started. So what's the resultant vector? We're starting at A and we're finishing at A. You might be tempted to say AA, but really the correct answer here is just 0, right? We haven't gone anywhere. So the resultant vector, the vector from the beginning to the end of the path, is 0. So it's funny because you're adding all these numbers up, you're adding all these vectors up, and what you're getting in the end is 0. But that's true, that's what it is. AD, so this last sentence. So you know what, I'm gonna actually clear up some space on here. I'm gonna erase this for the last one. AD, we're good with that. AD goes like that. Oh, let's choose a different color. Actually, let's not do that in green. Let's do it in yellow again. AD minus BD. Ooh, what does that minus BD mean? How can we subtract vectors? That's a little bit of a pain. It's different than adding vectors. I'm gonna tell you a little bit of a shortcut here. Instead of subtracting BD, remember BD is this arrow that looks like this. If I take it out of the place, out of where it is right here, BD looks like this. It's just a vector that looks like this, BD. So what does minus BD mean? Well, another way to think about subtraction is that you're actually just adding a negative, right? Because if, say, you're doing just a regular addition problem, 10 minus 5. Another way to think about this is just 10 plus negative 5, right? if we think about it for the same thing for the vector, instead of doing AD minus BD, we can say plus negative BD plus BC. Right? So we're just adding the negative vector instead of subtracting. So negative BD is the vector that goes in the exact opposite direction. So negative BD looks like that. And if you think about what it is, really what we're doing is we're just, instead of starting at B and going to D, we're going to start at D and go to B. So we're just flipping the arrow around. So negative BD is actually just equal to DB, right? So erasing this here, continuing with our path, negative BD is actually like saying DB, right? So that's the yellow arrow here that we'd be following. And now we can continue, plus BC. There we go. So how do we get from the beginning of the path to the end of the path? Well, the straight line distance between those two is just AC. There we go. So the trick here is don't subtract the vectors, add the negative vector, add the vector that's switched around. All right, going on to the next question. I have three vectors here and I want to add them together, A plus B plus C. So we can do this in a few ways. Let's just do it graphically first. So A plus B plus C, we know that means just to add those three vectors to follow the path. Now, you'll notice these vectors aren't connected. But that doesn't matter because vectors, it doesn't matter where they are. All you care about is the direction and the length of them, right? So let's start off with A. Let me start off with A. Go like that. That's vector A. And then what we're going to do that is we're going to add vector B. And vector B just clearly goes 2 to the right. Right? So that's adding A and B. We now have sort of another vector there. And then if we're going to add C to that, C is a vector that looks like this. It's basically you go down 1 and then 3 to the left. So if we're going to add C to that, it's like we're adding this to that. And we're going to end up right here. So C is this vector here. So really what we're doing is we're following this path. We're going from here, 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 here. But in terms of a resultant vector, it's like we're starting here and we're finishing here. So that is our resultant vector, right? So that's one way to look at it. And that's basically the answer. The answer is a vector that looks like this. We can call it R, right? And that's what it actually has in the question. They call it R. So that's the answer to the question. It's just a vector that looks like that. Now, if we wanted to apply some numbers to this, there's actually another way to do it where we don't have to sketch out the whole thing. So this requires us breaking down each vector into its parts and representing them all. And the easiest way to do this, I believe, is in matrix notation. So we did this in the last lesson. How can we represent vector A? Let's use blue here. How do we represent vector A in matrix notation? Well, remember it's the x and then the y coordinate. A doesn't go to the left or right, so the x coordinate 0. The y coordinate is going to be up 3. B is going to be just 2 to the right, so the x value is 2, and it doesn't go up or down. C, the x change, it goes 3 to the left and then 1 down, right? So negative 3 in the x direction, and then negative 1 in the y direction. So those are our vectors in matrix form. Now, the nice thing about this is that we can clearly see in total how much the x direction changes, right? So it's like the x direction isn't changing at all, and then it's changing by 2, and then it's changing by negative 3. The y part of these vectors, starting at 3, changing by 0, and then subtracting 1. So instead of sketching the whole thing out, we can actually write it out like this. We're really adding 0, 3 plus 2, 0 plus negative 3, negative 1. If we add those together, all we have to do is add the x parts of them and add the y parts of them. 2 plus negative 3 is negative 1. 3 plus 0 plus negative 1 is 2. There we go. There's our resultant vector. And if you look at our answer here, if we were to describe that vector in matrix form, what would it be? Well, it just goes 1 to the left, so the x value is negative 1, and then it goes up 2. I didn't really need to put the plus there, just 2, right? There we go. So that's two different ways to come to the same conclusion. One way by graphing it out and sketching it, and one way just by writing the vectors in matrix form and adding the x parts, adding the y parts. By the way, we do call this the component method. This is sort of the simple version of the component method. We'll get to the more advanced version in the next lesson, but when we mean component method, this is the method we mean because we're essentially adding up the x components of the vector and the y components of the vector separately. So let's try this question. R equals a minus b plus 2c. We're going to do it in both ways again and see which way you like better. So we're going to start off with a again. We're going to start off by adding a. A is just that, no problem. Then we're going to subtract b. What does that mean? Remember, what we can do is we can, instead of subtracting b, we can add negative b. And what does negative b look like? It's just the vector that's the opposite direction, right? So it goes 2 to the left instead of 2 to the right. So negative b just looks like this, right? So we're doing a plus negative b plus 2c. What do you think that means? Well, think of it as just c plus c, right? I'm going to do this off to the side over here. C we know goes down 1 over 3 like that. So that would be c, and then 2c would just be adding another c to that, right? Another way to think about it is just multiplying the length of c by 2. We keep the direction the same, so 2c is just the vector that's twice as long. And we call this multiplying a vector by a scalar. A scalar, remember, is just a number. So we're just multiplying the vector by a number. Okay, so back to our actual question here. A minus b plus 2c. And the 2c is going to be, well, there's 1c. And then 2c is going to be like that. So if we look at where we start and where we finish, we're starting here and we're finishing here. So our resultant vector, r, looks something like that. That's our answer. Now let's do the same thing with the component method that we did up here by breaking it down into matrix form, adding up the x and the y components. To do this, we need to know the matrix form of each vector, but you'll notice I actually used the same vectors in the previous question. So we know the matrix form of each vector is that, right? So the way we can write this out, I'll leave that at the top of the screen so we can see it. We can do r is equal to a, which is 0, 3, minus b, so minus b, and b was 2, 0, plus 2c, plus 2 times the whole vector, negative 3, negative 1. That's how we can show it. So in order to calculate this, I'll just show the calculation for this first one. We're going to do 0 minus 2 plus 2 times negative 3, right? This 2, think of this 2 as multiplying both of the components of the vector, right? Because it's basically doubling the length of the vector, so it's doubling the x part and doubling the y part. So really the operation you're doing here is 0 minus 2 plus 2 times negative 3. And for the y component, it's 3 plus 0 plus 2 times negative 1, right? So then if we simplify that, what are we going to get? Negative 2 minus 6 is negative 8, and then 3 minus 2 is 1. There we go. Now we can obviously check this vector here, r. Look, 1, 2, 3, 4, 5, 6, 7, 8, and then up 1. So r here that we got by graphing agrees with our answer that we got here using the vector components. You don't actually need to show this in-between step when you're calculating it because this is just simple calculator work. You can just skip right to the answer. You'll notice that this way is a little bit more clean, especially when we start to get numbers that aren't whole numbers. It's a little bit quicker to do it this way. So that's probably what you're going to do most of the time.